Thank you so much to everyone for joining us. We've got a really packed room now, so I'm really looking forward to a great day collaborating on all things phosphorus. So today is Alt-P Day, and hopefully you know by now that this is a shortened version of our alternative approaches to phosphorus removal at Rural Wastewater Treatment Works project. A little bit of a running joke is that we need to get catchier bid titles so that we don't have to say all of that. So Alt-P is what we became the name for the project. We've got a real mixture of people here today, some faces that I know, some that I don't, and hopefully will do by the end of the day. A mixture of water companies, technical professionals, supply chain, our regulators, so we'll keep on our best behaviour today, and yeah, lots of people from UU as well who've been involved in the project. So just to kick off, this is me, I'm Lisa Mansell, Chief Engineer for Innovation and Carbon, and I have worked with the team to deliver this project. I'm working with our central innovation team headed up by Kieran, who we'll hear from today. We've put get comfy, but don't get too comfy. We want you engaged, we want you participating. We've got a couple of activities to carry out, which you will be very happy about, but time to get a bit of your feedback and your opinions as well for the day. And we've got a bite-sized agenda, so we're going to run through the project. It's quite a chunky project. We've had 3 big work packages, and we're going to break those up with the activities so that you're not listening to us talking all day, and that you get to take part a little bit as well. This is our agenda for today. So we're going to have a little bit from me to start off with, and then we'll have our keynote speech from Mark Garth, our wastewater director and project sponsor for the Alt-P project. He's going to talk to us a bit about phosphorus removal and challenges for the industry. Richard will cover what is the Alt-P project, and then we'll have kind of run through the start of the work packages with Callum. And then we'll head into our exercise, our first exercise. And then Kieran Brocklebank, our Head of Innovation, is going to talk about adapting to the Ofwat Fund and AMP8 readiness. There's a nice chunk in for lunch, so hopefully we won't run over and take too much of that so that you can have a good network with each other. Back onto work package 2 around natural coagulants and another collaborative exercise. A little break this afternoon, and then we'll be into work package 3, where John Williams from the University of Portsmouth is going to talk to us about work package 3 on reactive media. One more exercise on the future of P removal to come, so we want all your good ideas and what we could be doing next as a sector. And then I'll just finish with some closing comments at the end. These are your speakers for today. Hopefully you know some of them, and you'll get to know the others as we go through. So we just wanted to do a quick section on knowledge sharing. This is an Ofwat innovation competition or innovation funded project. We're kind of really embracing the Ofwat Innovation Fund, and really it's driving us forward as a sector, really being able to kind of promote innovation and really deliver projects that we could never have delivered before on our own with our internal innovation teams, as great as we are, but actually working together as a sector in the Ofwat Innovation Fund. These projects are really revolutionising what we do, and hopefully you'll see today some of that. But knowledge sharing is a big part of the Ofwat Innovation Fund approach. We're really keen to kind of follow the 6 principles that Ofwat have put together, and Mark's here from Ofwat today, so you can challenge him on them if you think they're not the right ones. And we've been really doing that through this project, and hopefully you've seen some of that, seen some of the site visits that we've had with water company partners and with people outside of the partnership as well. We've brought people to site to see what's been going on. We've worked out, we've pretty much been on an annual conference run, going around telling everyone about the projects since the start, and that's one of those key principles. We did learn a lot from the existing information, so all the water companies were really looking at phosphorus removal technologies, and we'd done some horizon scans, and we'd done some internal work ourselves at UU, and Southern Water had been doing things already, and obviously things that Severn Trent and other water companies have been delivering. We took a look at all of that work before we got started, understood where people were, and understood the things that really needed a bit of support to move them from what we believed was really kind of market-ready technology into a ready to deploy, and some of that has happened within the project, and we're really thrilled to tell you about that today. We've, as I said, regularly been sharing our insights, and more recently we did a spring showcase. So we've got some of our spring colleagues here today, and spring are the sector support for knowledge sharing, and run a great platform and have a great YouTube channel that's broadcasting some of these projects, so make sure you take a look at that. We've had ensuring the sector is open and centralised, so we've really been open in this project. We've been sharing the data, sharing the project, sharing our progress throughout, and we've really kind of tried to target innovation insights at the right audiences. Hopefully that's some of what we're doing today, and hopefully we've got some of the right people in the room today to be able to share this learning and understand how we drive these innovations forward. We've been sharing successes and failures. We've had some challenges in this project, and Callum will do the honours of sharing some of those insights today. And empowering people to receive and embed lessons learnt from external sources. Well, I'm hoping that we're here to empower you guys to take some of this forward into your own businesses and into ours, you people, and also kind of sharing further across the sector. And really interestingly, we're seeing within this project and other projects we're delivering that innovation creates more innovation. So those partnerships and those relationships, they're driving new ideas to come together and really pushing us forward as a sector.
My name's Mark Garth. I'm the Director of Wastewater here at UU, and I've been the sponsor for this project all the way through. And when the team asked me to come and talk to you this morning, I started to reflect on my career and how phosphate removal has evolved during that time. I've worked in the sector for 25 years across 2 different water companies, and if I think back to, I used to be the works manager down at Warwick in Severn Trent, and that was one of the first sites back in the late 90s under the Urban Wastewater Treatment Directive. I then moved to Derbyshire, where we built a big, large biological nutrient removal plant. I think it was probably the biggest and probably the largest of its kind at the time. And then fast forward to sort of the late 2019, and we've Windermere here in the northwest, which I'm sure everyone recognises as a fairly iconic site, was one of our first low P sites. And if I think forward to 2032 at Eccles, which is nearby here in Manchester, we're going to have a permit of 0.1 milligrams per litre. So, you know, in that 25 years, we've already seen a vast evolution of how phosphate removal has changed and how technology has been used and innovation has been used to drive forward what's possible. But that's not going to be enough. We need to go much further. And the reasons are because, you know, phosphate is a key pollutant in the environment. So it's the most common cause of water quality issues in the UK. Under the Water Framework Directive, it's the #1 reason that water bodies don't reach good ecological potential. And as we all know from those all too visible signs of algal blooms, it can be a real cause of eutrophication and a real impact on not just the environment and the wildlife that is supported by that habitat, but also on tourism and people's ability to enjoy the water in their areas. We know that we've got a huge water industry national environment programme in AMP8, and that builds upon successive programmes in AMP7 and the AMPs that came before it. But phosphorus limits are going to be extended to more wastewater treatment works than ever before. Across the sector, over 800 wastewater treatment works are going to receive phosphate drivers and permit limit in AMP8, and that's a similar number to those that were delivered in AMP7. So we're effectively going to double the number of treatment works across the sector that are subject to tight phosphate limits. And we're going to go beyond those really large, technically advanced treatment works, and we're going to now extend into the rural areas and some of those smaller sites serving just small communities where even water supplies and power supplies and telecom supplies are a real challenge. So to do that, we're going to have to think differently, and the alternative methods for removing phosphate removal are a necessity to enable us to deliver that plan across the next 5 years. But also climate change is making life more difficult. So what would previously been an acceptable level of phosphate in water changes with temperature. So if I refer to Windermere here in the northwest, we've seen more than a degree centigrade change over the last 100 years in the temperature of Windermere. And so all things being equal, phosphate is becoming more of a problem, even if phosphate levels are not increasing. And that's set to be the case right across the northwest and particularly right across the country here in the UK as climate change evolves. So there's a real need to focus on phosphate. It's the right thing to do for the environment, but actually it's the right thing to do for the whole of the UK. We said we already do this at a very large number of treatment works across the UK. Conventionally, we'd do this using chemical dosing. We would dose either a mixture or one of ferric sulfate, ferric chloride, aluminium sulfate, aluminium chloride, or other metal salts. And there are several challenges with continuing that model. It becomes increasingly more expensive. Tighter permits require more chemical to be dosed. That chemical has side effects, more sludge being produced, more energy demand. It's more logistically challenging to get out to those more rural sites and to even just host the deliveries. How do you take an IBC of delivery at a rural site where you've got no forklift or no means of unloading the delivery, for example? And simple things like the safety related to these hazardous chemicals. How do you provide sufficient potable water for safety showers, for example, for the operations staff to know that if in the event of an incident with that chemical, they can safely douse themselves with water. There are resilience challenges with continuing to use chemicals. I sit on the operational strategy group at Water UK, and there have been a number of occasions in the last 3 years where companies have had to preserve and save and share supplies of chemicals because of interruptions in the supply chain. There are a limited number of suppliers in the UK and indeed across Europe, and any one force majeure or problem with their manufacturing process can lead to shortages right across the sector, even at the current supply levels. And there are carbon impacts, of course. The chemicals that we use are carbon intensive, particularly where they're a byproduct of the steel manufacturing industry. Every kilogram that we dose of ferric sulfate has an equivalent carbon impact across all of the emissions that companies emit. So as an example, if you use AMP8 Winnet drivers were all delivered using conventional chemical dosing, it would result in an emissions increase of 49%, so a very significant additional carbon impact just from doing the same thing and trying to scale it up, even if that was possible. I've talked about rural sites and why they present a challenge, many and varied a challenge, and in your company and in your area of the UK, the challenges will be unique to you, but there are some common themes. So smaller sites is a much higher cost per capita. So the technology and the underlying safety investment and logistics is the same, whether it's a very large site or a very small site. So the overheads and the cost of doing things become progressively more expensive the smaller site you're at. The operational complexity is a magnitude different to the complexity of the treatment processes that are already there. I've already mentioned that chemical supplies, electricity supplies, and the operational knowledge to operate some of these complex phosphate removal plants do not currently exist at some of these rural sites. So increasing staff capability and increasing the critical mass of staff who have the understanding and skills to be able to operate these kinds of plants is going to be a challenge for us, as well as delivering the assets themselves. The supply chain and the logistics I've already touched on. Longer transportation distances, up single track roads, in some cases without the capability to support HGVs, is going to be a challenge, particularly in some of those more remote rural areas. And the effect on communities, so whether it's increased noise from the traffic from the deliveries, tankers moving in and out because of the additional sludge being created, and that can be especially impactful in rural locations, and including that things like national parks, areas of outstanding natural beauty, and so on and so forth. All challenges that we deal with day in, day out, but we are adding to those challenges by doing more and doing it in a more complex way at some of those sites. But the good news is there's a solution to this. So we need to transition to more affordable technologies, low carbon technologies, and more sustainable technologies. And as a sector, we've all been working on this individually and collaborating, but this kind of collaboration project like the ALT-P project has somewhat revolutionized our approach. And the partnerships that have been developed both with suppliers in the supply chain, but also cross companies, are going to be essential to drive some of these sustainable solutions going forward. The leverage funding from the Ofwat Innovation Fund has really helped speed up some of the adoption of some of the technologies we've talked about today and that we're sharing today. But more than that, it's created a partnership, and it's created connections and contacts and relationships between suppliers and companies and between companies that will continue beyond the end of this project. So what we really hope today, and Richard will take you through the plan for the rest of the day, is that we are going to break out into a few sessions, and we're going to hope to start to build on the innovation that we've already seen as part of this project and use it as a springboard, if you will, for further innovation on pea removal going forward without the need for it to be structured so heavily under the Ofwat Innovation Fund. And of course, at the end of the day, it's all about sharing what we've learned. So even though there've been a smaller number of companies directly involved in delivering some of the innovation trials here, the aim is to share the outcomes of all of this right across the sector so that all companies can learn and move forward. So at this point, I'm going to hand over to Richard, who's going to take you through the rest of the day. Please get involved and enjoy the rest of the day here at Linglemere.
I'm Richard Clark, so I'm Programme Manager for Engineering Innovation here at United Utilities, and I've been leading the delivery of the programme, the ALT-P programme. 17th of September is great, it's ALT-P Day, okay, so please do write to your local MPs, get a national holiday, it'll make my day, it'll be brilliant, okay, we should all have time off. But ALT-P, this came about, all right, so going back to spring 21, okay, where Lisa, Callum and I were looking at different solutions for removal of phosphate from wastewater, and particularly at rural wastewater treatment works, so those smaller works below 5,000 population equivalent. I think it was Callum, wasn't it? You sent a pin out to the wider marketplace to see who would like to be involved in what was electrocoagulation, and that's what's formed work package 1 there. And just as this was happening, what we found was we had the Water Breakthrough Challenge 1 come along from Ofwat. So we thought, this is brilliant, because now we've got a way of funding this potentially if we enter this competition. And we started looking for more things to do. So then we looked at an Isle Utilities paper around chemical-free treatment, and we identified a few suppliers there. Okay, a couple are in the room. We've got Acorn and Veolia with us this morning. We identified a few other natural coagulants that we wanted to test. So that formed Work Package 2. Okay, thought, okay, we're onto something. And then we had the look of discussing this with our colleagues at Southern Water and the University of Portsmouth, and they mentioned that what the work they've been doing on reactive media. And it's case of, oh right, okay, well this could form another work package for us within our competition entry. So fortunately, the EC suppliers, so Power and Water, Cleaner, Hydro and Evergreen, were willing to join us and form Work Package 1. We had some good suppliers online for Work Package 2, and between Southern Water and the University of Portsmouth, we were able to form a package around reactive media. And really, well, the aim was to form a toolkit for the water industry to go to that kind of tries to move us away from using metal-based coagulants for phosphate removal at those small works. The project itself, it was £3.15 million when we started off. 90% of that came from the Innovation Fund. It's grown a little bit due to inflation, as you can imagine. Okay, so we have had a couple of inflationary increases on that. I think it's around the 3.5 million mark in the end. Mark, so you know Mark. We're coming in at around 5% under, okay, just to get completeness around there. On the right-hand side, you can just see the logos of the partners and advisory members and supporters that we've had along the way with ALT-P. It hasn't just been about UU, it hasn't just been about the partner organisations, it really has been a water industry wide approach to try and help us, as I say, move into a more environmentally friendly means of treating for phosphorus. How we've worked as a project team today is a bit about lessons learned, if anything. So you'll get a lot of information. Technically, Callum's going to come up in a little while and take you through the technical detail of it. But how we've worked as a team across the programme has really helped us. Okay, so you can see right in the centre of the slide there, the steering group members. We've had named individuals from the partner organisations on that steering group, and they've been the driving force behind the project, if you like. They've been very much directing the project all the way through. So for 3 years or so that we've been working on this, we've made sure that has been the central element to our programme management. And that's helped me, yes, absolutely, as the overall project manager. But it's also helped everybody in the work packages as well. So when our process technology team have been working at Walton, or when Southern Water and the University of Portsmouth have been doing their work down at Petersfield, it's been helped by this steering group, this central steering group, who've been able to answer both our commercial and technical questions. And I'm saying this because we've used this on our other off-water projects. So when we look at water industry infrastructure and biopolymers in the circular economy, we're finding the same thing. This is really, really good approach to these projects. It's helped us out immensely. We have named individuals, incidentally, because as you can imagine, if you look at all of the organisations that are involved in the project, it would be very difficult for an individual project manager to manage all of the individuals from all of the organisations that are in there. Those individuals named on there have been very helpful in reaching back into their respective companies and organisations and bringing the correct expertise to the fore. And this has helped us achieve our proposal commitments. So we set out and we said, well, we were going to do a 12-month trial of 4 EC systems. We've done that. Okay, we went beyond that. We were to remove phosphorus. We set a level of 1 milligram per litre. So all of the work packages have achieved that as well. We wanted to do a comparison of natural coagulants against our standard solution. Standard solution here being ferric sulfate dosing. We've done, you'll find later on when Callum takes you through all of the data and the graphs, we've done an immense amount of work within that area. And then as work package 3, we were finding that a lot of water companies were doing their own individual studies on reactive media, and we wanted to understand how we would go about bringing that together into a common approach. And that's what the University of Portsmouth and Southern Water have been doing. That's due for issue in October. It's one of our final deliverables for the project. The project actually completes in November this year, so you are seeing the back end of our project. But we've gone further than that. We've also developed further innovations off the back of this. So we've been able to combine the use of ferric sulfate and natural coagulants. So this is a key outcome that, again, the process technology team helped us to understand in the lab. So when we combined the ferric sulfate with the natural coagulant, we found that actually you get the timing right, it works better. Okay, so it's a really key step forward that they've helped us understand. We've also been talking to the EC providers about how we combine the EC and natural coagulant technologies as well, seeing if that would provide a more suitable solution in some cases. And you've got to remember, this is about different plants all over the country. Okay, this isn't just about a given location in northwest England. It's about how we shape these tools, how we use these tools to achieve the demands of the water quality demands at these different sites, but also the very kind of unique and site-specific requirements of sites throughout the country, those smaller sites. Great piece of work. We've had the help of our permitting team at UU to discuss at a national level with Natural England and the Environment Agency around the use of natural coagulants, so we can now use them as a business as usual approach to our phosphorus for our phosphorus solutions moving forward. And that's meant that we've been able to use it on a couple of AMP7 schemes already, and it is part of our solutions here at UU for AMP8. So it's really looking at scalability, starting to move what we've learned in the ALP programme out into the wider business and using it. That's everything from me. I'm going to hand over to Callum. He's going to take you through, well, he's going to take you into the detail, okay? He actually knows something. So I'm going to hand over to him, and he's going to take you through the detail of Work Package 1.
So I'm going to take you through a very, very quick summary of Work Package 1, which is our electrocoagulation work package. So 12 months of experimental data to talk through in about 15 minutes, so it's going to be quite quick. There's lots of graphs, which I'll try and talk you through as well. Work Package 1, we looked at electrocoagulation, and the idea of this work package really was to do a side-by-side assessment of 4 different electrocoagulation suppliers who were willing to get involved in the project. And you get opportunity during sort of the lunch break and the other breaks to go and have a chat with them. They've all got some stalls at the side of the room, so please take the opportunity to go and do that. They're across the top of the screen on the top right, so we had Kalina, Power and Water, Hydro and Evergreen that were all involved in this package of work. And you can see some photos on the right hand side of the screen where we had site visits to come and have a look at the pilot facilities, which all of our suppliers have been involved in as well. And there's a couple of photos in terms of what it looks like as well, but I'll go through some more detail as we go through. So in terms of what we were trying to find from this piece of work, we were really looking to understand, is it suitable for small works? Does it perform? So can it remove P? What are the iron residuals like? So can it meet the actual requirements that we need it to? Are there any specific influent criteria that are kind of really important for EC to be sort of suitable for certain works? And we'll talk a little bit about conductivity when we go through these slides, because we found that that was something that was really important. One big piece that we really wanted to understand was all around the O&M, so particularly the OPEX, the whole life cost. So what are the operator intervention requirements associated with the kit? We were aware that a lot of other short-term trials had been done on EC before, but never really for a full 12-month period to get the real picture in terms of the O&M requirements. And that was a key focus of the project. So we trialled it down at Woolton Wastewater Treatment Works, which is one of our wastewater treatment sites based in Liverpool, so Liverpool South. It's a conventional trickling filter site. There's no existing P permit there, so there's no existing ferric dosing, which meant that we had some P to try and remove. And we actually hosted both of our work packages on the same site, so you can see the natural coagulant trial area and the electrocoagulation trial area are both depicted on this graph. So just some photos and a timeline. So we actually started sort of the design and procurement process back in May 22. So it's been quite a long piece of work in terms of a trial. And you can see sort of from left to right the progression of where we started to where we ended up. So the digger on site was kind of, back in January 23 when we started kind of turning the area of site into our sort of semi-permanent trial area. The photo sort of in the top centre is what we ended up with. So we started operating that back in April 23. And in the trial area, we've got the 4 electrocoagulation suppliers and we've got a ferric control lane as well. And we opted to go for a settlement lamella downstream of every single lane. And it's not necessarily the conventional approach that we would take, but it normalised everything for us so that everybody had the exact same approach to settlement. And we can talk a bit around some of the limitations associated with that and why the results might look the way they do. And we ran that all the way through to sort of May this year was when we finished on site. So quite a long trial period on site, so around 14 months. And we tested a number of different feed sources. So we started with humus tank effluent on the advice of our EC suppliers, that being sort of the cleanest, the least fouled, so potentially the most efficient in terms of power consumption. And then we gradually moved it further upstream, so we ended up going for direct lift the trickling filters, so humus tank feed. And then we did a bit of an experiment where we actually artificially raised the conductivity by doing some salt dosing. And I can talk about the impact that had as well in terms of the overall efficiency as we go through the graphs. There are a lot of graphs, I should warn you now. There's a lot of graphs, a lot of data, and I'm going to have to do this pretty quickly. So the next one looks a bit messy, so I'll do my best. So this is our instrument data coming off the back of every single lane. So we've got, so we had Phosphax instrumentation on the back of each of our 4 EC lanes and our control lane. And I'm not going to kind of go through all of this data point by data point, but I think what it does is it tells a story. If we look sort of left to right, so this is starting back in September right through to March period. So that the purple line that you can see at the top, that's the feed concentration coming in. And then the other colours are kind of the various EC lanes and the ferric lane. So the ferric lane is the orange one. So if you just bear in mind, the purple one's the feed, the orange one's the ferric, and all the ones in between are different EC suppliers. So when we first started off, we had quite a lot of inconsistency in terms of performance, and you can see that with the way that the trend is kind of up and down, quite sporadic. We had some lanes that were removing some phosphorus, some lanes that weren't doing much phosphorus removal, but kind of at the start, the ferric lane was outperforming sort of consistently. And around sort of the Christmas period, after we'd learned quite a bit, we got to a point where we managed to achieve some better performance, particularly in a couple of the lanes. So if you look at the power and water and the Kalina lines, so the pink and the green, you'll see that sort of around November time, sort of the centre of the graph, they start to come down sort of towards the ferric levels. And that kind of remains sort of consistent towards the sort of the latter half of the trial. We did also see in the hydro lane, we saw some good performance, but it was quite inconsistent. So you can see there's some spikes which go quite low, but we saw they quite quickly spiked back up again. And evergreen, unfortunately, we never really got there. So a mixed bag of results, but it was really good that we kind of got to a point where we did see some consistent P removal across some of the lanes. This graph, these charts are quite interesting as well. So this is, on the left-hand side, we've got percentage removal of phosphorus based on our laboratory data, and this was taken directly off the back of the lamellas. And on the right-hand side, we've got percentage removal based on the instrument data. Now, the instruments themselves, they had a little filter upstream of the analyzer, which actually took out some of the solids. What you'll notice as you go from sort of the graph on the left to the graph on the right, you'll see on the left-hand side, the ferric is consistently outperforming all of the lanes. When we take the solids out, some of the electrocoagulation lane becomes very sort of competitive, particularly sort of towards the end of the trial, so the darker blue and the lighter blue. And even if you look at the power and water one, that starts to outperform the ferric lane, sort of once we kind of had the salt dosing online, once we'd removed the solids. And that was consistent with some of the solids performance data that we saw as well. For some reason, the solids didn't seem to settle as well in the electrocoagulation lane as they did in our ferric dose lane. I'm not sure if it's just down to the flock formation or whether there's something to do with, so you get hydrogen gas generation, which I'll come on to later in the slides, whether the hydrogen gas generation has something to do with kind of floating smaller solids rather than allowing them to settle. But there was definitely something in the solids which we managed to take out by the instrument data, and it kind of levelled it out in terms of performance for a few of the lanes. Can't talk about P removal without talking about iron residuals, and this was kind of quite interesting across the board. So I should mention hydro, which is the blue line, they dosed aluminium from the start. Everybody else chose to use ferric. I think, Kalina, you had a bit of a mix as we went throughout, but on this graph, it was predominantly ferric that was being dosed. It was iron plates. Now, if you look at the scale on the y-axis, some of these numbers are quite high in terms of the iron residual. So we had the power and water lane, which was very good at P removal, but we also had a bit of a risk in terms of iron residual. Should be said as well that even the ferric lane was fairly high in terms of what we would normally expect, and I think coming back to the lamella selection, that probably played some impact in that. But I guess the key thing is it's not as straightforward as perhaps plugging it in. You get P removal and everything's hunky-dory. There's lots of things to consider, and the iron residual is definitely a risk that needs to be taken into account when selecting the technology, and there is a range between the suppliers as well. One of the things we said we would talk about is O&M. So this is, we had power clips installed on each of the lanes. So this is power consumption across each of the lanes, so we can compare how much power was being used by each of the EC lanes, which would be quite an important factor for rural treatment works, which might not have, they might have limited power supply on site, so this is kind of a key consideration. And you can see again, there's quite a lot of variability in terms of the power consumption. So the orange line, which is quite flat, that's the ferric dosing lane. That was just a mixer and a dosing pump. So that was pretty consistent throughout. And you can see the red line, which is the Kalina line, that goes quite high, but it was getting very good P removal and quite good iron residuals. So there's a few things to consider. Are you more interested in power? Are you more interested in iron residuals? How low can you go on P? There's lots of things to consider. Whereas the other lanes were kind of quite comparable to each other, and in some cases we're consuming lower power than the ferric lane. So I did mention that we did do some salt dosing, and that was predominantly to raise the conductivity. So the conductivity helps in terms of the power, the electron transfer across the electrodes, which basically means that you can get a higher efficiency in terms of your amount of iron that you can liberate for the amount of power that you're putting into the system. So the darker blue line is where we were feeding it with humus feed without salt dosing, and the lighter blue lines is where we started dosing it with salt. And what this is actually measuring is milligrams of P removed per kilowatt consumed, so it's an efficiency rating. What you'll see across the board is that when we started to introduce the salt and raise the conductivity, every single lane, including the ferric, became more efficient. One thing to consider is that this is just looking at power, so this is not the full OPEX picture. So the ferric lane, this doesn't include the chemical costs in this particular graph, so we expect that they would kind of level out when we start to do that. But quite interesting in terms of influent criteria for electrocoagulation, conductivity, something which we think is really, really key and a really key finding from the project. So what else have we learned, and what are the potential barriers? So one thing that I have mentioned, but without going into too much detail, is we did actually have quite a lengthy shutdown on some of the systems after we had a hydrogen gas detection on one of the rigs. So we had one of the rigs which was in a shipping container with an open top tank, and I mentioned before, as a byproduct of electrocoagulation, you do get hydrogen gas generation. One of our process scientists who was working in the gas alarmed one day, and we took the decision to shut the trial down for a short period of time where we did a full investigation. Subsequently, we ended up fitting fixed hydrogen monitors with some kind of auto shutdown levels installed on each of the lanes. We did eventually manage to start back up after we'd gone through all the DESIR requirements, but something for everybody to bear in mind who is kind of looking at electrocoagulation, and I know that a lot of water companies are putting it in, is that you do need to do a full DESIR risk assessment before you put these things into operation. Photos show variability in design. I won't steal the thunder from the suppliers. They can tell you all about the designs during the breaks. So if you want to go over and have a chat, they'll tell you about kind of how the designs work, and I can see the Hydro bought some of their electrodes. But there was quite a variability in terms of whether it was handheld, sort of short plate life, versus something which needs like a lifting gear or a crane, which has a longer plate life. One thing which is a real key benefit is the fact that these things, they don't consume alkalinity. So on a lot of sites where you often dose ferric sulfate, it consumes alkalinity, which means you might need to put supplementary caustic correction in place. You don't need to do that with electrocoagulation, which is a real key benefit, both from OPEX, CAPEX, and health and safety. So this is just a summary, summarising some potential benefits, potential risks, and some next steps. So yes, EC offers chemical-free P removal, doesn't consume alkalinity. They do have quite a small footprint, and they can kind of be installed with a modular approach. There's no requirement for any chemical delivery area either. So one of the things that Mark talked about earlier was around the risk on communities. You don't need to do that with electrocoagulation. And subsequently, you get a reduced health and safety impact. Something else which is quite key as well, you get quite a lot of impurities when you dose chemical. You don't get that with the electrocoagulation. On the flip side, there's quite a few risks that we probably still need to overcome. So the high metal residual is something which can't be ignored and needs to be taken account for. So we think that you would definitely need some kind of downstream protection to manage that risk where you would consider EC. Power requirements vary, so you need to make sure you get ample power supply on site. There's a passivation impact. So passivation is just the name for fouling of the plates in electrocoagulation. What you tend to see is that when that passivation layer starts to build up, it increases the resistance, which means that your voltage starts to go up. That essentially drives when you need to replace your plates. We saw on some systems where the passivation happened within a couple of days. We kind of got to a point on some systems where it was a bit more consistent, but that's a real key consideration. In terms of scale, we were focused on rural treatment works, so they're very suitable for the small sites. In terms of the overall conclusions, EC, it does remove phosphorus. It works. It removes phosphorus without requirement for chemical. But we think there will be some kind of downstream protection required for sort of either low P or metal carryover. And in terms of next steps, there's a bit more work to do to kind of consider factors like ORP. So we've done some reading around ORP and the impact that can have on the reaction from EC. We think there's some further work to do combining with TSR, and other water companies might be looking at that. I think we're still evaluating our cost and carbon, which Rowan's helping us with. In terms of outputs, we know that lots of other water companies are placing orders, and they've all been to site to kind of come and have a look at the kit and ask us lots of questions. So from a knowledge sharing perspective across the sector, we've done that really well, especially with companies that are putting it in. And then the other thing which I'll touch on, and Richard mentioned, is the potential to combine it with some of the other approaches that we've explored, so particularly the natural coagulants. I think you find some of those combinations quite interesting as we move through.
Good morning everyone, I'm Kieran Brocklebank. I have the privilege of being the Head of Innovation here at United Utilities, and I've been involved from day minus 473 on the ALT-P project. I must admit, when Mark Garth stood up earlier and he introduced this whole section, saying, I've been thinking about ALT-P and I wanted to reflect on my career. And I was thinking, God, was it really that bad? He's going to hand his notice in or something. So I'm very pleased that you made that connection for us, Mark, because making those connections is a really, really important part of innovation. It's why we're all here today. It's no good a single water company just operating on their own, in silo, working with a single supplier. Let's get diverse voices, let's get out there, let's get AMP8 to be a much more collaborative environment. What I wanted to do then was just spend a few minutes telling you a little bit about how United Utilities goes about innovation, and then making that connection to leveraged funding and the Ofwat fund, and maybe sharing with you what has it been like as a water company, a client, using the Ofwat Innovation Fund. What's it been like as a lead partner on this project, and maybe take us away from just the technical aspects of ALT-P, and maybe just elevate us a little bit and see what's the big learning that we can take from here, applying it to lots and lots of other places. And I'd like to share that learning with you in a very open and transparent way. So the first thing to share with you is, we as United Utilities, we're one of a number of water companies here in the UK. We happen to be quite one of the larger ones when you measure it in different metrics, but we're in a changing regulated sector, a sector that sometimes has an unfair reputation, a sector that is sometimes difficult to show people all the hard work and all the efforts that people go to with the best spirits in mind. And we've always had a focus on innovation, but I need you to know we're going to have a continued focus on innovation. Innovation doesn't happen just by chance. Just bringing you 50 odd people here today, it needs management, it needs coordination, it needs filtering, prioritizing resources on the right things. So we have, like many other companies, not just water sector, but like many companies, we have a model. We know that we'd love innovation effort to maybe encourage and engage more people, get more people connected to the exciting world of innovation, that world of continuous improvement, of change, of scrutinizing problems, unlocking what's the blockers, how can we scale this up, how can we roll it out. We want to engage more people. And here at United Utilities, we have quite an open innovation model, meaning that we don't just focus all of that time and attention just with a small handful of R&D people in a single department. We think the answer is out there somewhere, if only we could ask the right questions to the right people. And our open innovation model actually encourages more suppliers, startups, university spin-offs, academia generally, current suppliers that we want to improve their performance with us, brand new suppliers who are working in other sectors quite happily, but could we persuade them to come over to the water sector? We need those new suppliers, we need those new voices into our sector. And of course, what our innovation model primarily is trying to do is to try and go fast and get us to adopt proven ideas. That is not easy. Let me tell you, as the head of innovation here at United Utilities, it isn't easy to do that every single day. You can't just take an idea and try and drive it home in a large organisation, particularly not one that has the regulatory barriers and the regulatory tolerances that we have. But maybe we could start to prioritise some of our efforts to try and get adoption faster than we would do. And we believe innovation is infectious. We think talking about innovation is helpful. We think if you'll have heard from a few of the speakers this morning, you know, this particular project, we're spinning off, we're learning new things that we could be doing. Let's add this to this now that we've learned that. And this infectious nature, we're going to snowball this initial kernel of an idea, could grow and grow and grow, and it could be something really, really special. Here in UU, we have a number of methods about how we go about innovating, and some of the household names that you may have heard of is our Innovation Lab program. We've led 5 of those. We've reviewed over 1,000 supplier ideas. We've done 35 world firsts, proven 12 new concepts. We've got loads of adoption. We've got financial efficiencies, and it's been quite a good model for us during AMP7. We have a lot of effort as well on our employees. That's the pink logo there. So how can we train more people to look at their own work area and try and unlock the problems and the bugbears that they have? Let's teach them, you know, lean process techniques, and we call that performing together. And we have the green belt all the way up to black belt type community, and that's led by our central groups as well. And of course, something that's come along just in the last few years that we see as a blessing and a curse, of course, is our access to the leveraged funding. You know, this great opportunity for us to grab that, to connect the water innovation strategy to those projects, and that we could lead a few and we could support a few others, and we can take the learnings from everyone and we can bring them into our organisation. So how has that new fund surfaced for us? What kind of impact has it been having? Well, if I ask you to stay on the left-hand side just for the moment, what we're finding in AMP7 is, if I just take a particular subset of our innovation investment, and what we've found is we're doing much less just on our own these days, a smaller percentage, compared to working with others, with partners, whether that's working with leveraged fund partners or whether just collaborating with other water companies, whether that's globally or here more locally. And is it about us working in collaboration with lots of suppliers together? And then right at the top there with the biggest circle is the Ofwat connection. And in Ofwat's annual report in the summer, they confirmed that UU is connected to the most winning projects, which was a nice accolade to have. And we want to maintain that high reputation in terms of, we believe this is a great opportunity. And for the right projects, with the right teams, with the right ideas, we can use that to great effect. What we found then, if I look at the period of AMP6, we did very, very little percentage spend in this leveraged way. Yes, we were collaborating with others. Yes, we would, in an ad hoc fashion, tap into other leveraged funding streams. But really what we've done, the Ofwat Fund and other funds, has allowed us to really direct our attentions and grab those opportunities, finding the right partners, building the right ideas, and turning those into deliverable projects. But along the way, if I now ask you to look to the 6 boxes on the right-hand side, what have we been learning as we've been going? How have we been changing? How have we adapted? Well, firstly, we've had access to this kind of offshoot through the Ofwat Fund called the Discovery Programme. We've used that as an opportunity to get some of our talent connected with that world. we're learning lots more about suppliers and innovators who've got low market readiness ideas. Wow, we're really watching, where is some of this ideas, where are they blooming? How do we keep track of those? How do we keep tabs on those people? How do we support them? And of course, what we've found there is us supporting the Discovery Programme. We need to choose carefully who the mentors are that we send in to help those suppliers. Those suppliers are fragile, they're vulnerable, they have an emerging idea, they might be a startup, they might be brand new, they're certainly not market ready. So to throw them into a large organisation with all of our day-to-day processes, with our commercial teams and our swarming all over these people, we need to protect those ideas and protect those suppliers. So we've chosen our mentors really well, and they've been super effective in supporting the Discovery Programme. We're hoping that there's more discovery during the AMP8 Innovation Fund, and the signals are suggesting that we're going in that direction. So we're going to use that as an opportunity to broaden who we use to support. Why don't we get some of our emerging talent? Why don't we coach them? Why don't we have better mentors for better ideas? let's go top right, processes to find and submit bids. Of course, as a client, we've always enjoyed suppliers having to do all the legwork and providing quotations and here's a proposal, not quite right, go back and do another one. And it's been great sat on our little hill here, getting all these supplier things in. Well, I'm afraid the shoe is on the other foot now. We're having to do lots and lots of that work, and I tip my hat to any suppliers who has to go through this bidding process and quotations, because we've learned tons. Callum showed a graph earlier of all that kind of phosphorus stuff. That's our blood pressure when we're doing this bidding process, linked to my little smartwatch. So those processes of how do you find all those ideas, how do you filter them, which ones are the ones that are really attractive to other partners? We might have an issue or something that we want fixing, but does everybody in the sector? Because that's the qualifying criteria. And of course, when we're finding and submitting bids along the way, you've got to choose the right partners. And we've been learning along the way all about partner selection. How do we choose the right partners for some of these things? How do we surround those partners with the right support? Adoption. So of course, when these projects are finished, UU happens to have, in the terms of the current portfolio, we've led 7 projects, 2 of which we finished a couple of years ago. And both of those have been adopted by United Utilities. We've got financial efficiency return, we've saved carbon, we've got new learning, we've improved our AI models as a result of those projects, and we've shared all of that learning with others, hoping that they pick those up and do the same type of rollout that we have. And of course, we've got a few more that are underway. Today we're hearing about Alt-P, where we've proven some concepts to the satisfaction of water companies, and UU has decided we now know enough that we can turn that into real solutions in our capital programs. And I think that's a brilliant step forward. So we won't shy away from trying to adopt where we can. And what we're really pleased about in the AMP8 fund is that there are some signals that maybe there's even more opportunity to get adoption over the finish line with some extra help from the leveraged fund. In terms of learning, wow, we could take all day sharing our learning just on Alt-P alone, and we've shared some already, not just technical results, but you know, what's it like working with partners? How do you, if my model is accurate there, where in the very first circle, this is about you working on our own, well, you've got total control there, haven't you? You can go as fast and as slow as you like. You can make wild decisions on a Monday and implement them on a Tuesday. You know, you're really, really the driving force. When we work in collaboration with others, there are other partners who also have a say. And of course, one of the big learnings is, how do we find those partners? How do we find partners that we know, that we like, and that we trust each other? And all of those 3 are absolutely vital in partner selection. And we've learned a lot along the way about the different types of partners that have grown and worked with us. What are the responsibilities of being a lead in this world, a lead partner? You know, on the Alt-P group, there are a number of other water companies who are partners, equal status. And then you've got this odd arrangement called the lead partner, who is slightly first amongst equals. But what responsibilities do we actually have, and how do we report that? Can we make decisions on behalf of the group and overrule people because we're in the driving seat? And I'm the poor bugger who's got to report back to ChallengeWorks and Ofwat about when there's delays and things like that. So how do we jostle and juggle all of those lead partner responsibilities and take advantage of being a lead partner as well? And one of the things that we've really learned, if we go down on the bottom row now, bottom left, collaboration. You know, moving from a UU-only world to one where we're working with other partners, it really, really does open up and test your collaboration muscles. And we've never really managed that before. We've never really acknowledged we must work hard at collaboration. You know, we talk about partnership, don't we, all the time. We talk about let's collaborate, let's cooperate. But why aren't we putting effort into upskilling people to be able to do those things? And that's what we've been doing at UU. The first few projects that we've done, we've embedded collaboration into that world. So yes, talking about technical results. Yes, talking about how do we connect systems at Woolton Wastewater Treatment Works. But we also have a focus on, can we as a partner group, can we collaborate better together? And so we've used some survey techniques, we've carved time out in project steering groups and technical groups on this project and on others. And I would say now that we've had a good few attempts at doing this, we're getting really, really good at spotting, are we displaying the right collaboration behaviour amongst all the partners? Because let's recognise some of this imbalance. We've got a very large client as a lead partner. I hold all of the Ofwat fund money. And then we've got suppliers wanting that money, wanting to move the project along. And it's quite a power imbalance, isn't it? We've got large client, smaller supplier. We've got lead partner to partner. We've got lead partner to Ofwat and Challenge Works. All these relationships have all relied on collaboration. And I must take just 20 seconds just to congratulate the Challenge Works approach to this, because along the way with this project, you heard about some delays that we've had. You've heard about how we've changed scopes on some of our other projects. The openness of being able to ask questions to Challenge Works through Ofwat and others, the openness to be able to do that has been very, very healthy. And it's allowed the projects to thrive. It's allowed us to reach these kind of stages where we have brilliant, tangible results that we can share with everyone. And we're hoping that people start adopting them. But it comes from that collaboration. It comes from that openness. Let's work together. Speaking of collaboration, it's one of our ways that we want to be more transparent. How do we say to people, if you want to be a partner with us, these are the rules. We will always use a standard legal collaboration agreement, and we'd like you to see that up front. We would like to do this on payment terms. We would like to work with you on collaboration. We would like these principles about how we work together. And we're setting out our stall earlier and earlier with partners now. So, you know, when I talk about can we find partners who know, like, and trust us, of course that's two-way. They have to know us, they have to like us, and they have to trust us. And we just think if we're more and more transparent in that, then we're going to find the right partners and find the right ones to collaborate together. And one great example of this collaboration, which shocked me, to be honest, when we did the first bid, was the openness of our supply chain in ALT-P, the 4 electrocoagulant suppliers. The fact that they were able and willing to work in this very open way, side by side on a single site, all visible to all of them all the time, in the spirit of sharing. We were talking about how other units were performing in front of everybody. I think that's a great sign for how this project has been successful, and we'd like to continue that for future projects. We hope that supplier behaviour is something that we can mimic on other things. And of course, just in terms of more transparency, of course we want to say to people, what are we working on? What do we need to solve? How can you help us? And we're going to make ourselves even more open to that. So let me just pick up on something that one of the groups fed back on, which was about attitude to risk. And I really resonated with that feedback, because innovation investment is all about a balanced risk approach, and we happen to use this portfolio model that you can see on the left. You know, in terms of time along the bottom and kind of how radical is an idea, let's acknowledge, shouldn't we? You know, an idea which is more radical to me needs more processing, it needs more support, it needs more thinking than a proven market-ready one. You know, this client is the last in the whole sector to actually buy one. Why is nobody else doing it? Never mind fast follower, slow follower. So you must acknowledge that difference up the left-hand side in terms of the radical nature of this. And we've just got 3 definitions for that. If it's something that's of low complexity, low disruption, and it's happening soon, then that's in that kind of incremental world. And one example of that is we have artificial intelligence every single day is telling us what the pipe condition is in our wastewater sewers. And that's happening faster than humans can do it. It's happening more consistently than humans can do it. And our productivity there has massively improved, so we can give a better customer service for lower cost and all of those environmental improvements about the condition of wastewater sewers. It allows us to make those interventions earlier. Where are we with ALT-P? We're kind of categorising ALT-P as something that we could really start taking advantage of very soon. So that breakthrough idea, it is different to our traditional and conventional methods of treating wastewater. It is different in terms of the opportunity. Mark was talking earlier about how on earth are we going to get these chemical deliveries down these tiny country roads to places that don't have electricity. How are we going to do that? So maybe some of this Alt-P world is going to open up and snowball into, maybe there's some real small modular self-powering units that might come on the back of this. And finally, if I give you an example of radical nature, well, we've publicised quite a lot through LinkedIn and at conferences and other publications, press notices and things. We've got something really, really different. Can we convert biogas into graphene and to hydrogen? And if we do that, we're going to create these alternative materials. What are we going to do with them? Who should take them from us? Who should give us some revenue? Who should help us dispose of them properly and in a sane and compliant way? So we've got this model about how we categorise all this investment, and the Ofwat Fund is no different. We're looking for breakthrough and radical ideas that we can really drive home in this risk-based approach. So let me finish my final slide, because I promised you that I'd try and connect that to AMP8, and I speak on behalf of all water companies here, but I'm going to speak with more confidence, of course, about how United Utilities is approaching this. Well, there's 6 things that I'd love you to come away with remembering about what we're doing here. I think the first is, we've got a showcase event like today. It's a little unusual to have 50 people wandering around United Utilities for this thing. But I can tell you, on other days of the week, there is innovation activity going on in every pocket of United Utilities. North, south, east, west, in water, waste, in customer, in every department. You can lift a rock and you can see people innovating every day. And I think that's fantastic. It's just what we do around here. It's what our leadership expects of employees, and we incentivise that and we reward and we recognise great innovation behaviour. It's hardwired into our values. But of course, not everyone every day is dealing with Alt-P, these breakthrough ideas. Not everyone every day is dealing with super radical ideas. So sometimes you need specialist teams. You need those teams who can protect ideas, work with uncertainty day in, day out, won't kill an idea on day 1, maybe kill it on day 31. But you need all of that protection of those things. And if we do that in a risk-balanced way, it's made us slightly more successful. Of course, our employees is our fantastic asset. Their ingenuity, their drive, their passion for improvement, and you've seen some of it today with our speakers. That group of people will continue and continue and continue. We'll have even more people fully trained in how to unlock problems and local problem solving. Our talent groups, our graduate community, they're going to be accelerated into leadership positions. They're going to demand that their new teams that they're leading will follow this innovation process. And in terms of fast acting, we want to be known as an organisation that when we see an idea, we give fast feedback on it. Whether that's a successful outcome for the innovator or not, we're going to give fast feedback. We're also going to try and capitalise on trends and opportunities when we see them. So if we see someone else doing something great, how do we grab that idea, bring it in, pass it to the right people and help that idea navigate its way around the corporate labyrinth of a large company? And we've been quite successful with that. And of course, we want value from innovation. It's tempting only to talk about financial returns, of which we've delivered a lot from being innovative. But what about the other benefits, these multi-capitals, which is more and more prominent in how water companies report on their performance? So, lots of these innovations are improving our customer service, our operational performance, certainly on environmental. You're hearing all about that today. And something that goes a little hidden maybe is social value. The growth of what water companies are going to do in AMP8, the size of those programs, we're going to need more and more people, selfishly for us, here in the Northwest. We're going to need more and more people in the Northwest, spending their money in the Northwest, contributing to the Northwest economy. And I'm really pleased that one of our innovation programs, the Innovation Lab, because we've worked with startups who've relocated to the Northwest and they've grown on the back of proven idea with us, and we've introduced them to other water companies, and that's spiraled off into more and more contracts for them. Their business has grown, and they've recruited 35 new jobs in the Northwest just from our Innovation Lab program. And that social value sometimes gets missed, and maybe we shouldn't. Certainly some of our other Ofwat funded projects, we've got whole social value work streams about how are we going to capitalise on this great innovation, and how are we going to convert that to social value. Well then, bottom left, shared challenges, shared solutions. I mentioned earlier we have an open innovation model. Put simply, we think the answer is out there somewhere, or at least the people who might have the answer is out there. So if we could only ask the right question at the right time to the right people, maybe we would get great and better ideas coming through that we can handle with care. And of course, we're getting ready for our AMP8 delivery. We're waiting for the final determination numbers. And what does that mean for us as a company? What does it mean for the sector? How do we connect all of our innovation portfolio that we have today? How do we connect that with delivering better for customers for AMP8? And how do we go even further? And that's why I'm delighted that we're looking to the Water Breakthrough Challenge 5 opportunity and even more Ofwat Innovation Fund in AMP8.
Afternoon, everybody. Hope you've all had a nice lunch, suitably fed and watered. Lots of networking and collaboration over the lunch break. Hopefully you've had a chance to go and speak to some of the EC suppliers as well. I'm going to take you through Work Package 2 now, and then I think we've got another activity straight after that, and then another break. And then I think we'll be moving into Work Package 3, sort of the early part of the afternoon. So without further ado, I'll move into kind of the Work Package 2, which was all around natural coagulants. So this piece of work really started a few years ago before we wrote the Ofwat bid on a piece of work that we commissioned Isle Utilities to carry out for us, and that was all based around alternative or chemical-free treatment options for use across the water sector. And we partnered on that piece of work with Welsh Water, Scottish Water, Northumbrian Water. Within that report, there was a section all around natural coagulants and their potential for pee removal. So we actually used the shortlist that was generated from that report to reach out to the supply chain and see who wanted to kind of join our project, our ALT-P project. And thankfully, 5 suppliers did get back to us. So we tested 5 different products. So we started off in the lab. So our process scientists, we've got Ian and Sue in the room. So they did a lot of really good work in the labs, which helped kind of make this work package as successful as it was. So initially, we were looking at can we dose the natural coagulants on their own to remove phosphorus? And what we found was that they were very, very good at solids removal, but they didn't do much for the pee. So we kind of took that learning and we thought that there might be something in it with the solids. And we started to combine it with ferric, but at reduced amounts to see if there was a synergistic effect. And when we did that, the results were absolutely kind of really, really excellent. With massive flock formation, really fast settlement, but we also managed to reduce the amount of ferric sulfate that was required by about 50%. One of the other interesting things that we also found was that the supernatant in the jar tests, so that the iron residual was very, very low compared to when we dosed ferric on its own. So we took all of that work in the lab and we decided that there was merit in kind of taking that combined approach to a pilot scale. So we did this down on Woolton as well, same site as we did the electrocoagulation trial. So we did the jar testing back in summer 2022 and we actually completed this package of work in November 2024. And there were 2 products that we tested in the lab that we took forward to pilot scale testing. We've got both suppliers in the room today. So we tested Hydrex, which is supplied by Veolia, and we also tested the BWAT, which is supplied by Aircon Water, produced by a company in Spain called Servieco. So the pilot plant itself, we were taking screened crude as our feed source, and we ran that through a pipe flocculator to promote mixing with a number of injection points, and we had a settlement lamella to kind of replicate a settlement stage. And similar to Work Package 1, we had a control lane, we had an experimental lane. So I don't know if you can quite make it out on the photos, but there are 2 lanes there. So in our control lane, we just dosed ferric sulfate, and we dosed that at 4 molar ratio, which was what our jar testing told us we needed to dose that to get down to 1 milligram per litre. And then in the experimental lane, we dosed half of that amount, supplemented by, I think it was 100 ppm of the natural coagulant. And there's the flow diagram I've just described. So I can kind of flick over that. So the next few slides, again, I've got lots of graphs and data that I'm going to try my best to talk you through. So this one's showing some impact on phosphorus performance, and it's probably worth noting that this wasn't a how low can you go trial with regards to phosphorus. It was, can we get the same result with regards to phosphorus performance with less ferric? The settlement lamellas and the control were probably less than ideal, which so the results should probably be taken in the context of the pilot equipment and the sort of the quite basic control that we had available. But the merit of the control then is the fact that we can see how the experimental then did compare. So on the left-hand side in sort of the green heading was the BWAT performance. So this is where we had the control then at 4 molar ratio, the experimental then 2 molar ratio supplemented by 100 ppm. And in both graphs, the feed is the dark blue colour, the control lane, which is just ferric, is the orange, and the experimental lane is the pink. So sort of moving from left to right with the data points, we can see when we started off, the experimental lane was outperforming the control lane sort of considerably. And then as we sort of moved towards the middle, we saw that the performance started to tail off, and the control lane did start to kind of outperform the experimental lane to some degree. We weren't getting kind of really low levels of P in either lane, but I think we can put that down to sort of the lack of control that we had. It was quite basic. But there wasn't that much difference in it. Similarly with the Hydrex, again, that was a 4 molar ratio in the control lane. Experimental was 2 molar ratio plus 100 ppm. And what you'll see in the Hydrex experiment is that it was pretty much neck and neck throughout the duration for both the control lane and the experimental lane. So that's with 50% reduction in ferric sulfate. In terms of suspended solids, this is when we started to see outperformance in the experimental lane, and this is where the natural coagulants really start to come into their own. So you'll see sort of both graphs, the impact of the BWAT on the left, the impact of the Hydrex on the right. The suspended solids performance was significantly better in both lanes. Some of the levels that we were getting down to with a crude feed were less than 25 milligrams per litre suspended solids coming off the back of the lamellas. So quite a good effluent quality on what would kind of be the equivalent of a PST settled effluent. And then the other thing, which is probably the key learning from this piece of work, was their impact on the iron and the iron residual. So the feed iron that you can see in both graphs is the blue line, which is kind of really close to kind of zero, not much coming in. The orange line is what was coming out of the ferric dose lane, so some quite high levels of iron coming out in terms of the residual. Now what you can see with the pink line is the impact of the addition of the natural coagulant. It pulls that iron residual down to sort of consistently less than 4 milligrams per litre. So we're iron compliant at a primary dose location by using the addition of natural coagulant, and that was with a reduced amount of ferric sulfate as well. So we've got a summary of some percentage removals here, which I'm not going to read every single percentage removal line by line, but I've just highlighted the ones where the experimental lane outperformed the control lane. So again, the green is the BWAT, the purple is the Hydrex. So not focusing too much on the actual numbers, but what you'll notice is that a lot of the outperformance was actually on the experimental lane. So whether that was BOD, solids, alkalinity, generally the experimental lane did outperform it. In both cases, the P was pretty close. But yeah, overall, the other benefits, and particularly the iron and the solids, is where we saw a real benefit. So we took that learning, and we took the learning from work package 1, and we decided there might be an opportunity to combine the two approaches. So if you remember before lunch, when I was talking about electrocoagulation, one of the kind of the barriers with electrocoagulation was the high iron residual. The work package 2, one of the key selling points was the impact on bringing that iron residual down. So what we decided was that there might be a real opportunity to combine the two approaches and see whether you could kind of get the best out of both of them when we kind of combined them. So we actually dosed some natural coagulant into the power and water lane for about a week at the end of our trial, very short trial, but the power and water mixed tank was an open mixed tank, so it made it quite easy to do that. And we saw some really promising results. So In terms of, there's a few performance graphs here. So top left is total P. The feed is the dark colour. The effluent is the light blue colour. So when we started to kind of add the natural coagulant, we managed to get some samples which were less than 0.5 milligram per litre coming out. I think some of them were pushing 0.25. But yeah, we saw a real step change in terms of the P performance compared to what we saw before with the EC. Again, with the suspended solids, as soon as we added the natural coagulant, we were getting down to less than 5 milligrams per litre in suspended solids. And the real key was the iron. So you remember some of the numbers that we showed before, and you can see it on the first data point there, the effluent's up at 20 milligram per litre iron residual. When we added the natural coagulant, it brought it down to less than 4, probably less than 2 consistently. And the graph on the bottom right of your screen, so the highlighted area, you can't quite make it out in the bottom right, there's a step change. So this is showing power consumption. So this is showing power consumption before we added the natural coagulant and after we added the natural coagulant. What it really allowed us to do was to reduce the dose rate required by around 75%. So we actually managed to reduce the power consumption by 75% compared to using the electrocoagulation on its own. And that has lots of other benefits because it extends plate life, it reduces your OPEX, and it basically means that you're getting a lot more efficiency out of a plate. So massive impact on the OPEX point of view. I'm just going to share a few slides now where we've also done some other further work with natural coagulants with that iron benefit in mind. So we've actually we've done quite a lot of work with the regulators. So we've been in conversation with the EA it probably took about 12 months, something like that. I've just listed out some of the information that we had to do that. So we've had to provide sort of process assurance documentation to provide them with all the data from the trial. We've also had to do some environmental assurance, and we actually had to consult a third party to do that for us, APEM, including invasive non-native species assessment. We've GCMS the products. We've had to GCMS crude and final effluent on the sites when we've dosed them, and we've had to do an intensive 3-month sample period at 2 sites, which you can see on the screen, Dudden and Madeley, and feed that back to the EA. And eventually we got to a point where the EA have approved both the use of natural coagulants for use at full scale. So we've done a lot of hard work supported by our reg team as well to kind of get to that point. And that was all done at a national level. So that was kind of on behalf of the wider UK water sector. So that wasn't just a UU activity, that was kind of water sector wide. So we've done some trials at Dudden and Madeley, and these are both AMP7 schemes. So the Dudden is getting a 0.7 P driver, Madeley getting a 0.25 P driver. And for both schemes, there was a TSR that was in scope. Dudden's around 500 pop, Madeley's around 6,000 pop. For both sites, the approach we've taken is we've combined ferric sulfate with natural coagulant at the primary point of application, so just dosing into a primary settlement tank. And we've got some results and graphs to show you on the next page. So at Dudden, we've managed to get the total P to around 0.28 on average against a 0.7. The iron residual we've managed to get 1.12 on average, and the key selling point for both Dudden and Madeley, so Madeley 0.15 milligram per litre average against a 0.25, the iron average 0.23 and a 0.5 95th percentile. For both schemes, we've done that without the requirement for a TSR. So for both schemes, we're managing to de-scope the requirement for TSR from the capital solution, and this is going to go in as the capital solution for both these AMP7 schemes. The graph that you can see just shows some of the results for iron and P. So you will see on the Dudden, so the iron residual is the orange, the phosphorus residual is the blue, and the dotted lines are various combinations of molar ratios and natural coagulant dose rates that we tried on site. But you'll see that consistently when we added the natural coagulant, particularly after sort of the third dotted line in, the iron really came under control, and the P was really, really good. We did have one exceedance on the iron, which is worth pointing out because you can see it on the screen, and that was down to a blockage on site which caused some short-circuiting of the process. One thing that's worth mentioning that we did see at Dudden is formation of a biological slime. which did cause some additional O&M requirements on site. So it is worth calling that out as well. Similarly for Madeley, we've just been dosing into the primary tank, and we've managed to get the effluent quality down to 0.25 milligram per litre. Managed to de-scope the requirement for TSR on that site. And what we've also managed to de-scope is the requirement for alkalinity correction, because the natural coagulant doesn't consume alkalinity at the same rate as ferric sulfate does. And I think at Madeley that's with a 2 molar ratio supplemented by 100 ppm of natural coagulant. So really, really good story, really positive outcome from the project where we've taken the learning, applied it on site, and it's actually going in as 2 capital solutions in AMP7. And we're now looking to roll it out as an approach in AMP8 as well. So this is just a summary slide. So benefits of natural coagulants, risks and next steps. So the big benefit that we saw was related to the iron residual and the solids performance. Something that I didn't show on the graphs, but yeah, the natural coagulants do consume some alkalinity, but they consume less alkalinity than we see with ferric. So there's a potential benefit there as well. We see some benefit to reduce load on downstream assets because the BOD's solids performance is so good. Could you free up headroom on downstream trickling filters, ASPs? It does still require ferric, so it does still require a combination. So when we were talking about chemical deliveries previously, that's not necessarily got rid of that, but there is a place for it, we believe. And we're still working on the operation, on the overall carbon impact, but we believe there's a reduction in operational carbon. In terms of risks, I've highlighted the regulatory approvals that are required, so we've done a lot of the legwork for that, but it's just kind of a word of caution to anybody that does want to use these products. You do need to inform the regulator that you're planning to do so with a robust plan and an approach to it. From a unit cost perspective, they are more expensive than ferric sulfate or metal-based coagulants, so that you do need to do an overall costing exercise to determine whether there's benefit there. And there's a few bits and pieces going on where the suppliers are kind of carrying out life cycle assessments for us to kind of really work out an emissions factor associated with them. The carbon's still a bit of an unknown. One thing that we have kind of understood is at the minute there's limited supply available, so if everybody in the whole water sector decides to start ordering this stuff, we might quickly run into some supply issues, so that's something that needs to be thought about as well. And I mentioned the slime. So when we formed the slime, it was also blue-black in colour. So there is an impact on colour depending if you don't get your dosing right. But we think it's more superficial than having any other impact. So yeah, as a conclusion, we think natural coagulants offer really excellent ion control. The real big benefit on the capital programme is potential to de-scope the requirement for TSR. When dosed in combination with ferric, you can get down to quite low levels of P as well. We think there's some further work to be done combining EC plus NC, where you can eradicate ferric or similar altogether, and our initial work suggests that that's a really good approach. It's something that we want to explore a bit further. Probably worth mentioning that the testing that we didn't really vary the natural coagulant dose an awful lot, so we think there's a bit of a sliding scale where you add more ferric, you need less natural coagulant, and vice versa. We need to do a bit more work to understand what those combinations look like.
I'd like to thank United Utilities for hosting this today. My first time in Warrington, so I've achieved another first. I'm John Williams. I'm Professor of Environmental Technology at the University of Portsmouth, and I'd like to present the work package 3, which has been done in association between us and Southern Water, and unfortunately Della Martin from Southern, who's been very involved in this, couldn't be here today. So this work package was looking at reactive media. There's obviously been a lot of work done in this area over the years, and United Utilities have led lots of the full-scale applications of this. But in the context of ALT-P, there were several barriers which were identified for the adoption of reactive media. One was the range of media which are available. The media which have been trialled today all have limitations one way or another, the key one being the requirement for pH amendment afterwards. Secondly, there's been no real standardization of the lab testing. Lots of lab testing done at different scales, different sizes, some with different sewage types and some with synthetic sewage. So we were looking at trying to standardize an approach to testing the media and also generate some data around potential new media. Secondly, the engineering design, how these media would be used in practice. So we've been looking at how they might be applied in terms of filters, wetlands, and so on. And as part of that, we've held a workshop hosted by Narinda at Stantec, where we looked at the potential scale of operation, what sort of size of works, what sort of engineering application this might be done. And thirdly, trying to look at the cost modelling. It's a bit daunting coming from outside the industry, but just trying to understand where reactive media sits on this economic scale of things. So work package 3, it's led by Southern Water with University of Portsmouth, and we've been looking at these different aspects of this. I'll go through some of the things that involve lab testing, but one of the important things as well, we've been trying to establish a mobile test rig which could move between different sites with different water chemistries, different phosphorus concentrations to try and standardize an approach to field testing as well as lab testing. Just get a plug-in for our facilities. This is our environmental technology field station where the work's carried out. We're very lucky we have a field station facility at an operational sewage works. We rent some lab space from Southern Water and some outside area, which means we can do full-scale trials with real sewage with on-site laboratories. So we have our own test beds which we can use for wastewater. Unfortunately for phosphorus trials, this works has ferric dosing. So the trials we're going to report on at the works here, not the ones in the field, we have to dose phosphate back in. So it's a little bit of the only downside of having that site. This is the timeline. So we've started off developing some column trials in the lab, trying to standardize the approach to column trials, and we'll talk a bit about that. We also started speccing up the reactive media, it's a containerized system, container at that time. And also we started off doing a horizon scan and a consultation with industry about what media out there, what media might be most appropriate. Coming through, we've set up various trials, column trials, indoors and outdoors on site, and reported on that. And we are developing this containerized system. We saw on the first slide the ALT-P open day we had, where we hosted visitors and showed people around that containerized site. That container is placed at another sewage works nearby, a small rural site, West Marden, for various reasons, also because there's ferric dosing at our main site. So we wanted something which was more real-world conditions. So if we start off with the column trials, first of all, we did horizon scan. We listed maybe 25 different media which were out there, and we went out to the water industry partners in this project and asked people to rank them and come up with the media which they thought were most interesting or most appropriate. We decided not to test any of the media like the pollinite, which has been used in practice. We wanted to look what media were there which were new, which might offer new possibilities. And we decided we had two types of trial. One was going to be our low-rate indoor column trials. And secondly, we had outdoor columns with high-rate media, which were going to be pumped and operated at much shorter hydraulic residence times. Throughout this, when I say I'm going to refer to empty bed contact time, you can report the results of reactive media in a variety of ways in terms of mass removed per mass of media, mass removed per surface area of media. We've decided that these are going to be in something, a unit process, and so we deal with volume of material, and so express it as empty bed contact time. Indoors, in the low-rate media, two media came out of the horizon scan. One was Phosgrain. This is one Danish Technology Institute. It's calcite covering silicon dioxide. And also, we've been doing some work with calcining seashells, cockle shells, over the last few years with MSc students, and that was deemed attractive by the people who responded to our horizon scan. And we built columns in the lab, and we were operating these at 3 different empty bed contact times, 6, 12, and 24. We also had some high rate columns outside with much finer grain media, operating at between 2 and 2.4 and 7.2 minutes empty bed contact time. And we were testing these 4 media here, bio-free, catalytic carbon, GH101, and a zeolite-based media. And these were outdoor columns. These were taking much higher flows and operated under backwash conditions when they reached a particular head. I'll deal with the high rate media first, mainly because this caused us lots of problems with solids. We had a real nightmare trying to manage solids going onto these media. Mainly we have pumps at different stages of the wastewater works, and our final effluent pump sits in a well which accumulates solids. So here we have these outdoor columns which we were operating, and at the very low hydraulic retention times, 2.4 meters, we were just clogging them up. We put all sorts of measures in place, copa sacks, stockings, all sorts of things to try and manage the solids onto this. In the end, we had a small pilot reed bed left over from another project. We used that as a sacrificial pre-treatment. But we also were testing these media, and we decided to stick the 7.2 minutes, the slowest empty bed contact time. So we've got some results. We've got some quite reasonable results for the GH101. That media was keeping the phosphorus down to less than about 0.1 milligrams per litre over about 25 days. But I really, the problems we had with controlling the flows on here, I wouldn't want to bet on the mass balance of this. This was causing us all sorts of problems. Luckily, we had our engineering design workshop. We had 15 representatives of 8 water utilities, and everyone said, no, we wouldn't use reactive media in this mode. So we parked the high rate media at that point because people said that wasn't going to be an application. The low rate media in the columns in the lab, we set up these columns. They are 600 mil high, 130 mil diameter. That gave us, for the media we were testing, over 20 times media diameter to column diameter. There's some debate about what that ratio should be, but 20 plus seems to be a level which doesn't give you too much wall effect. And unfortunately, the cockle shells, which came out very highly rated in horizon scan, had performed very well in the lab with dosed water, and we put them in the field, didn't perform very well. So on the top graph there, at the beginning, you can see that top line is the influent, P, and that purple line just beneath it is the cockle shells. They weren't giving us much removal at all. So we parked the cockle shells. And then it turned out that one of the media which we put into the horizon scan, Phosphorus, by PET, who were introduced to the British market, had been scored lowly because people assumed it was associated to their other product, Phoslock, which is lanthanum based, and that is why people had not scored it well in the horizon scan. But it turns out it wasn't. It was actually an American product, Poseidon pellets. They were bringing into the UK market and badging by a different name. Subsequently, they went bust. And now this media, who's supplied by Water Warriors in the UK, they're introducing it to the UK. So we replaced the cockle shells at that point with the Poseidon pellets stroke Phosphlow, depending what you know it as. So from that line onwards, that vertical line onwards on the graph, we've got the introduction of the Phosgrain versus the Phosphlow. And as we go down through there, there's no labels on that, which isn't helpful. But basically, A, B, C are the Phosgrain, at 24, 12 and 6 hours empty bed contact, and D, E, F are the Poseidon pellets at 6, 12 and 24 empty bed contact time. And you can see across there, we've extended this further now, we've got further data to add to this, we've kept these columns running, but for over 200 days all of those were keeping the levels down below about 0.2. At that point, at around 200 days, the 6-hour empty bed contact time, Poseidon pellets, Phosphorus, started to break through. The others carried on at a very low level, and over the whole of that trial there, we've got for the Phosgrain, a median at 24 of 0.15 milligrams phosphorus, at 12 hours 0.22 milligrams phosphorus, and at 6 hours 0.48 milligrams total phosphorus. Starting to get a little bit of breakthrough at the end at the 6th. And for the Poseidon pellets, at 6 hours the overall mean was 0.26, and at 12 hours the overall mean was 0.36. So those media are all getting down below 0.25, and particularly the Phosgrain is keeping the concentration down below a mean of 0.15 across that years of data collection in the lab there. Now, a couple of things of interest. First of all, the Phosgrain was performing the best, but it still gave an issue with pH elevation. So the Phosgrain, we have pH above 9 there over the first 200 days. We're still getting good removals after 200 days, but it would need some sort of pH amendment as in the existing media which are being used in practice. The Phosphorus stroke Poseidon pellets, now it's quite exciting, it almost immediately dropped below 9, so this media could be used without subsequent pH amendment, which takes away one of the issues of using reactive media. The only other problem is that these media, the size ranges are down from like 2 to 6, so they're smaller than the size media which has been used for the pollinite. So they would need some sort of solids protection probably. So we're trading off whether pH amendment versus solids protection is required. But if you've got a very low solids effluent, the Phosphorus could be used directly. The Phosgrain, we're getting very good phosphorus uptake capacities in terms of grams per kilogram, milligram per gram. We've carried this on, and the Phosgrain's gone up to over 20 milligrams per gram. So this is much, much higher, almost an order of magnitude higher for what we've detected on some of the other commercially available media. So this means the beds could be sized smaller. So there's a real trade-off here between size of bed, pre-treatment, post-treatment in the economics here. Here's the trial unit. We've got 3 large columns, and in here we've got the Phosgrain and the Phosphorus stroke Poseidon pellets. We put some cockle shells in. I did some more work with some MSc students, and we changed the calcination temperatures and pre-treatments and thought we'd cracked it. And then we put a column of cockles in here, and again, they haven't done anything. It's really disappointing. Really want the seafood to work. We've replaced that with another media. We will report on that subsequently when that's installed. And we also have a intermediate scale filter here, which we filled with Poseidon pellets. This is receiving final effluent from the works. All of the influent and effluent are being monitored for turbidity, pH, phosphax units doing total P and SRP, and these are being online monitored. Here you can see some of the instrumentation. Unfortunately, this has been an absolute nightmare to maintain. We imagine we pop along once a week, top up the reagents, do a bit of maintenance or whatever, but we've had people down there nearly every day with different alarms going off, so it's been quite an intense experience, and Adela and Janine, the research fellow working for us on this, have been spending inordinate amounts of time giving tender loving care to this containerized system. So the idea of it being moved around between different sites is a challenge. I don't know if we're quite there yet with the technology and the monitoring and the online instrumentation for this level of sophistication. We have got all the bells and whistles. We can check. I'm not going to do a live demonstration because it probably won't work, but you can see we're getting feedback from all of these different columns and all these different. We haven't got a. We've had lots of interruptions on this data. We need to go through and just block out when we had failures and what we were monitoring. So I haven't got anything to absolutely report on that today. But we are getting good removals from the two media, pretty similar to what we were seeing in the lab. So those two media do offer a new perspective, a new set of options for the water industry. Now they are commercially. Water Warriors are bringing this over to the UK. I know they're speaking to some water companies. I know that buying it, we bought the last bulk sack of them in the UK and they charge us an arm and a leg, but I'm sure if there's a bulk supplier, commercial supply, they'll bring their price down. And the Frost grain is made bespoke by the Danish Technology Institute. So again, I think there's a commercial, people have to speak to them and work out what the production cost and what the bulk cost is, because the cost we paid probably doesn't translate. In terms of engineering design, I said we had the workshop hosted by Stantec. We've defined some population sizes. Generally, we're looking at a sort of filter-based approach, and we've got various media characteristics and general layouts which we've come up with. We're also looking at potential for recovery. We've been doing some experiments around how we might recover people. That was beyond the scope of what we were doing with an ALT-P. Obviously, if we can get that circular economy aspect of recovering the P and getting it back to agricultural land. That's why the cockle shells excite me a lot, because obviously they're used as a soil amendment anyway. If you've got P on them, it could be a direct use without an intermediate stage of either physical or chemical recovery or rejuvenation. Cost modelling, again, that's been quite a learning curve. Unfortunately, we started this project on our staff in the School of Civil Engineering and Surveying. We had a quantity surveyor who'd had previously worked for Thames Water, had water industry experience. We thought, great. Of course, this project took, from the day it was announced we'd won it to when everything was signed off, it was a year, and at that point he decided he could learn lots more money outside the university, so he left. We've been going through this with people who aren't, with a QS who isn't a water industry specialist. We're starting to understand some of the variables around sizing of cost of media and replacing media, and comparing that to some of the reported figures in the some of the water industry spending plans, and trying to understand how these fit within the externalities, because of course ferret costs aren't just putting in a tank and a pump. There's all the other things you've been hearing about, the health and safety aspects, the knock-on effects on sludge and other aspects of pH amendment throughout the works. So, in conclusion, very low peak consents can be achieved by reactive media. This is quite nice. We did a PhD on reactive media before we did this, so this wasn't generated during ALT-P, but this is a section through some reactive media under SEM EDS microscope, and that green line around the outside of that section through the media at the top, you can see the phosphorus. There's a mixture of precipitation here and absorption, but you can probably see the calcium phosphate deposits all around the surface of that section of the media, but you can see at the bottom the enrichment of the phosphorus on the surface layers. So we definitely are getting phosphorus attachment there. So we have got a media now which are available, which perform well, do not require pH adjustment. Cost is going to be the deciding factor, and that's all about the economics, which I hate to say it, I'm not an expert on, and after dipping our toe in the water, I don't think I want to be an expert in, because it's not. Of course, the effluent solids management, what you're feeding onto this. If we start to go down to these media, 2 to 6 mil, we are going to have to think about the solids management going onto there. Do we have a sacrificial reed bed? What do we put up front? and the replacement period and phosphorus recovery, that's to make this the technology we would hope it could be in terms of stopping phosphogeddon and all this running out of fertiliser. We need to be further research in that area. The container, I think we did a great demonstration of the engineering potential, but there needs to be probably some more robustness in the equipment before that could be deployed at scale. But we are starting now to get some really good results out of that, and we're going to keep running that to the end of the project to get as long a data set as we can, and that will be reported in the final report.
So yeah, just a summary to say thank you so much for all coming here today and taking part and engaging in the exercises. And just as a bit of a recap, we started off with Mark, and he told us about the phosphorus problem. He told us about the challenge that seems to not go away, and we've come up with new solutions, and we're dabbling in those, but on the whole we're generally sticking with those iron or aluminium metal based coagulants to solve the problem for us, and it's unsustainable, and we still need to look for alternative solutions. We've talked about a couple here today, and hopefully you feel a little bit more confident in applying some of those, or you might have more questions that have come up that we can explore in future innovation projects. Both Mark and Kieran actually talked about the importance of collaboration, and today is a good example of that, how we've come together today to explore some of that, and how the ALT-P project has brought people together to collaborate and brought up some new solutions perhaps that we can look to adopt, and there's solutions within the project that we are already adopting. Hopefully we've shared how important we think the Ofwat Innovation Competition is, and I'm not just saying that because Ofwat were here, because they've all left and gone on a train, but it really is driving us to do much bigger innovation projects than we ever have done before, giving us the space to do that. We're setting ourselves up as water companies to deliver within the competition, and I just found out we've got to go and pitch for the next round tomorrow, so Ali, I think we need to get busy overnight. So yeah, really I think for us these competitions are driving us to be more innovative, to design much bigger collaborative innovation projects than we have before, and hopefully there's more of that to come. Our speakers, so Callum and John, have both talked us through the technical aspects of the ALT-P project really well, summarising about a year's worth of work, or over a year's worth of work, in 15-minute slots is a bit of a talent, so thank you for that. And yeah, I think really we've shown that the outcomes of some of these packages are really ready to apply, and hopefully we've given you a bit of confidence that these can be applied, and we are already adopting these at United Utilities and some of the other water companies already. Hopefully you found the collaborative workshops interesting, and you've got to meet new people you've not met before, and you can make new connections that you can take away. But I think there were some common themes that came out of there around things like having a kind of wide stakeholder confidence is key to us taking forward these solutions. So we talked around how do we support operations to deliver these solutions. We talked a lot around kind of getting support from our regulators, and that our regulators actually need us to support them to feel confident about it. And I know there was quite a number of comments around how the Environment Agency specifically need to be a bit more flexible in permitting. Well, they have in this project. They've really supported us, and we've done a lot of work with trying to share the confidence that we've got in the trials and been able to take that into full scale, and we've done that really quickly, and that's because we've been able to do these full scale trials for a period of time to give the EA and Natural England confidence in the solutions that we've put forward, and that's proven successful in our programme now. We also have talked a lot about how we can kind of overcome this route to adoption by sharing, so that's what we're here to do today, and we're sharing on innovation projects, but we should be sharing a lot more on everything we do. And I know a lot of people in the room try to coordinate us as water companies to share, and we don't always do that. But hopefully kind of the challenge that we've got ahead for AMP8 drives us to needing to do that, and we do share a lot more. So yeah, I hope you've had a good day, and I hope you've got something to take away, and we've really enjoyed sharing the project with you. And just thank you very much. Thanks for taking part. Thanks everyone.